All right, recording is rolling. Welcome to another fine day, Thursday, August 17th. We're going to take a couple of days to do this project, Geneva Drive. You guys got lots of fun materials on your desk. You guys got cardstock, you guys got glue, you guys have some other things too, scissors, string, protractors. Okay. So I'll walk you guys through that, what we're doing, but give you guys a look at schedule around what we're doing. Monday, Tuesday, I want to do trigonometry and vector components with you guys and fill in some blanks with like maybe algebra and dimensional analysis type stuff. I want to do that again. I haven't given you guys any like real serious homework yet, so what's probably a good idea to do is continue exploring those materials on Google Classroom, and especially if you're just a curious, ambitious person, right? And the more you're familiar with those, I know there's tons of stuff on here. It's probably what's a good thing to do too, right? The more familiar you are with these materials on Google Classroom or those pages that I gave you guys back last Thursday, yeah, the more it's going to help you out as the semester rolls along and we get more deeper and deeper in this class. Okay. Solar challenge. Did I throw you guys this solar energy question yesterday? Yeah, I did. Okay. Tell you what, since I'm making a recording right now, and this might be the one that goes on Google Classroom, let me recap this one. I'm mostly throwing this towards my AP students, but you know what? If you guys want to solve it too, I mean, it's a fun challenge. I've had one student solve this so far correctly. So yeah, I'll probably go over the solution on Monday, maybe real fast. And if you solve it by then that could be really cool. So the question here at the bottom is like, how much land area would it take to meet energy demand for the entire United States with just solar alone, right? So all you have is solar energy. So let's say you go out to Arizona, you just buy a bunch of land, you have a bunch of solar panels. How much land area do you need? Right? Now, I gave you guys some numbers and some assumptions on it. Right? This is what's called a back-up envelope calculation. That's to say that we're skipping over maybe some engineering technical difficulties, like how do you store it and blah, 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 right? So don't worry about that. This is just a very mathematical problem that could give you maybe a ballpark answer that's pretty close to the true value and tells you something about it, right? All right, so here's what we're working with. Here's the energy demand for the United States. At least this was true a few years ago. 25,000 terawatt hours per year. Okay? So capital T tera is 10 to the 12. That's one of the posters we went over the other day. Right? So it's also there hanging on the wall by the door. Right? Tera is 10 to the 12, just a prefix. Watt. Right? If you've never, I know we haven't gone too much into this class, so might not be familiar with these units, but I bet you guys have seen like a 40-watt light bulb. 40-watt light bulb. So what is watts? Watts is a rate of energy, right? It's a rate of energy. So if you have a 40-watt light bulb plug in, it's continuously pulling 40 joules per second off the grid. That's what a watt is. It's a joule per second. It's like energy per time, right? Even if you don't know that, you can still solve this whole problem with just that railroad method of unit analysis. It's just a giant unit conversion problem, right? But maybe helps to know the context. Hours, that's a time unit. Years, that's a time unit. Hey, a time unit, a time unit. Do you think somewhere in those railroad tracks you might have to reconcile those time units? How concentrated is solar energy? The fact that Earth is so far from the sun. Now, if you're standing out 12 o'clock noon in the summer, you might get a number like this, maybe 1360 watt per square meter. You guys see those floor tiles? Can you guys count 3 by 3? You guys see 9 floor tiles, 3 by 3? That's pretty close to square meter. Not exactly, but pretty close. Okay. So 12 o'clock noon in the summer, got 1360 watts continuously flowing onto that area. But half the time it's night. Sometimes it's cloudy. Sometimes it's rainy. So kind of an average value is this right here, 400 watt per square meter. 1 kilometer is 1,000 miles. 1 square kilometer, 1,000 by 1,000, that's 1,000,000 square meters. Right? This might help you out possibly. And one last curveball at the end of this problem. Suppose your solar panels are only 20% efficient, which is kind of a realistic number. So 100 watts might be landing on the solar panel, but only 20 of those watts are actually useful on the grid. Okay? There's enough info lying around where you can answer this question. It's a real challenge question. Again, I'll probably briefly go over the answer on Monday, I'm thinking. Yeah, have fun with that one. All right, so let's do the main thing we're doing today, this Geneva Drive. Now, you guys were watching that animation while I was running attendance. I don't want to flip my screen yet just because there's something weird with Zoom. Like, I haven't quite figured out. They changed something weird over the summer. So I'll flip it, but I only get like one flip. Right. But here's a model that I created. Now, this is similar to the animation. It has some differences. It's not exactly the same, but it serves the same purpose. Right? You guys see I'm hand powering the gear on the right, and that's causing an incremental motion of this gear on the left. Right? So I have continuous motion on the right turning into incremental motion on the left. Right? This is a Geneva Drive, or at least one version of it. Right? Now, where do you think that might be useful? Okay, possibly some kind of lock, maybe. Oh, you said clock. Yeah. Actually, Geneva, guys, Geneva. That's a city in where? And Swiss are known for making clocks. Yeah, tick tock. Bet there's a Geneva Drive in that right there. Geneva Drive right here. Right? What's going on? How about you pop in an old VHS tape? How do you turn a roll of film into 30 frames per second? Or suppose back in the 1940s, go to the old times, go watch a talk together. So go to the movie theater and you're watching the film projection. It's all smoky room. You guys get so it's one of these click clacking in there. Right, turn roll of film into 30 frames per second. How about suppose it's 20 years from now and you're a mechanical engineer and you have a job to design a factory for a bottle filling company. Say, when you fill this line of bottles, next bottle, next bottle, next bottle. Look at that, right? Geneva Drives. Right. Okay. What do I want you guys to get out of this project? You guys get to exercise your spatial skills today. You guys get to think in 3 dimensions. You guys get to work in teams. Get your hands on all these materials. It's just a paper and glue project. You guys get to take something that initially at a glance looks complex and break it down into its fundamental parts, right? Maybe that's a big theme in this class, right? Is that there's so much crazy, complex, cool stuff you can do with physics, right? It's just like everything in the built world, you have to have some kind of fundamental physics for. But at the end of the day, everything just boils down to Newton's 3 laws of motion, right? That you just like put on a page, right? So back to the first principles type, right? So let me flip my screen over, which you kind of get one shot to do until I figure the zoom out a little bit better. Flip my screen over here. Right. Okay, so there's the animation that you guys were just looking at. Now, see, their drive has like 6 teeth and 6 gaps, and mine had 8. That's okay, right? They have 1 peg. I had 3 pegs. Right? Just as long as serves the function to turn continuous motion in 1 gear to incremental motion in another gear. You can add a different number of teeth. Again, they have 6. I had 8. Some students earlier were mentioning water wheels, and that reminded me of an old clip from a documentary series in the 1970s called Connections. So I pulled this up. So let's run this real fast. I had a couple of students earlier today mention water wheel, and I got to break up this clip. I can't miss this clip. So here we go. Oh yeah, that's right. Beautiful system. All right, so here's how we do this. The first few minutes of class, I'm just gonna leave that animation up there and you guys can work with your teammates and figure out how to make that. Every few minutes in class, I'll pop in and give you guys some hints and start constructing one myself. But I wanna give you guys some time to see what you can come up with by yourselves, right? You might have a little bit different techniques to construct those different parts or exactly how you wanna put it together. So I'm gonna pause this recording and go for it.